Um, as I make an announcement, the first slide of today's the lecture notes, because of the weather issue, the building where we stored this Raspberry Pi and also where the department is located, and there is also the contact points. The secretary, Maria, should come. But because of the weather, the building was completely closed whole week last week, so no one can access. But last night I heard from the university facilities. They said they will reopen from today. I didn't check whether it is open because I'm here with you, right? Tomorrow I have another class at upstairs, so I may be able to see if it is really, really ready. So online students, yeah, you guys need to get your Raspberry Pi this week. And then first Raspberry Pi related homework assignment due will be 2 weeks from today. So next week, we'll work on the Raspberry Pi installation and configuration. The completion of installation and configuration will be the next homework assignments. That is the first Raspberry Pi, and also a little bit of Linux related homeworks. Due is 1 week after that, so I think it will be Sunday evening before we have a Monday class begin. Okay, therefore, rather than moving forward with those who receives here face-to-face classes, your kits, while some others not yet. Therefore, we're going to push our technical sessions from next week. So 1 more week, relax time. And I included quite a few video clips. So you may learn a little more about the Linux from these video clips. So many, I think more than 5 video clips available and included in this lecture notes. They are talking about why Linux operating systems, and also a couple of applications where Linux can run, Linux can contribute, and also artificial intelligence. AI is booming, right? That affects you guys, particularly those who are majoring computer science, coding classes. That affects my coding class as well. But Linux operating systems, quite safe, right? That is operating systems. So how AI run in Linux, that also a very, very important topic. And Linux deployment. Linux deployment, that is really, really advanced tech. I know some of you already know, but most of you guys may not, which is called the Docker. Docker. Have you heard of a Docker? Yeah, Docker container. Ooh. Nicole knows everything. Yeah, he's working for a data center already. If we are lucky and if he is willing to, we may hear some story about real data center from Nicole later. Okay, that's what we are going to do today. So there's no homework, number 1. relax, sit back, and watch the videos. But thing here is this: when I run this, I tested this morning, but it says, "Oh, you need to verify." This guy told me, "I'm not a robot." I do not know how can I verify I'm not a robot, right? This is simply so. What I did here, once I have this, then I can copy the URL and then bring it here.
Hello everyone, and welcome back to Destin Learning. In this video, we are going to look at an overview of the Linux operating system, outlining some brief history and some of the use cases for this very popular family of operating systems. Let's go ahead and get started. Linux is a free open-source OS known for its stability, security, and versatility. It powers devices from smartphones to supercomputers. Developed by a global community,
Wait a
it can be
minute.
modified and
Did I
distributed freely.
record already?
Linux started in 1991 by Linus Torvalds, inspired by
Let me
Unix.
check.
It was released under GPL, allowing open contributions. Over time, it grew into a robust OS, supported by a
Which
global
means
community,
it's being
including major
recorded, I guess, right?
corporations. Today, Linux powers servers and cloud
Let me check.
platforms. Linux
Actually,
is
one more
highly
time.
versatile,
Yeah,
excelling
already
in various
recorded it.
areas. It
Oh,
dominates the server market, powering
good.
over 90% of the top web servers. It's ideal for hosting websites, running databases, and managing cloud infrastructure. Popular web servers like Apache and Nginx run on Linux. Linux is widely used in embedded systems, such as routers, smart TVs, IoT devices, and automotive systems. Its lightweight and customizable nature allows developers to tailor the OS to specific hardware, making it ideal for resource-constrained devices. Linux, while holding a smaller desktop market share compared to Windows and Mac OS, is favored by users who value privacy, security, and customization. Distributions like Ubuntu, Fedora, and Debian offer user-friendly interfaces and extensive software, making Linux a viable option for both personal and professional desktop computing. Developers prefer Linux for its flexibility, open-source nature, and support for various programming languages and tools. It is ideal for coding, testing, and deploying applications due to its strong command-line interface and package management systems. Linux is the leading operating system in high-performance computing, powering over 90% of the world's supercomputers. It efficiently handles massive workloads, scales well, and supports specialized hardware, making it ideal for scientific research, simulations, and data analysis. Linux is essential in cloud computing, with major providers offering Linux-based VMs. Its open-source nature supports containerization and orchestration technologies like Docker and Kubernetes. Linux has grown from a small project to a major technology force. Its open-source nature, stability, and security make it ideal for servers, supercomputers, and cloud infrastructure. Linux is versatile, impacting personal desktops, software development, and data centers. Its significance in computing continues to grow. Well, that's all for this video. If you like this video, please click the thumbs up button. If you'd like to see more videos like this, please consider subscribing to our channel. That's all.
That's all for today's class. Okay, next one. So I summarized a little bit in this way. So what makes open source operating systems powerful? There's a transparency. Okay, there's no hidden places. Anyone can inspect how the system works. So security flaws can be found and fixed all together by collaboration. No hidden backdoors. No hidden backdoors. That is very, very important. I think literally you may feel what the backdoor means, right? But throughout this, your stay in Mercy cybersecurity program, you may practice some of the backdoors. If you're a manufacturer, then you can imprint some of the backdoors. So that is the security hole. The attackers from outside can intrude inside your device. It could be anywhere. If it is embedded in your home appliances, it goes into, and also your anything, right? If you have your home smart surveillance systems, then it's not only you protect your home, but your enemies, your attackers, may be able to see inside your home. So in the future, your home may not be yours. It'll be the attackers, right? If your home door lock is controlled by some of the devices, then your home door lock may not be yours. Your home is not yours. So anything, if it is running over Windows, please do not buy it. Do not install it. Only if it is running on Linux, you can do it, because as you can see there, transparencies, okay? Keep that in mind. Freedom to modify and innovate. Okay, back to number one. How can you see then if there is a backdoor? You're not a manufacturer. Even if you open the device, there's a circuit board you cannot do. That is a software usually, right? You cannot see what it is. How can you see it then? One simple way is that you need to set up your router. Maybe another Raspberry Pi, you set up your router, and all of your devices go through your router into your home Wi-Fi router, real router, okay? So you have some bypass, and then you can investigate packets that destination packets from any devices that coming into your Raspberry Pi. Then you can search from there if it goes to your enemies' countries, whoever, right? Or your enemy friends. You can check it. Technically possible. Okay? Manually, it is real hectic. So you have to do a little bit of codings. Python coding can do. Very, very efficient. Okay, move to the point 2. Freedom and modify innovates. So you can do, you can strip the OS down for embedded systems, harden it for secure servers. You need to have a little bit of skill sets. Customize it for AI, robotics, and networking labs. Okay. And your Raspberry Pi can connect it to the cloud infrastructure, supercomputers, robotics, cybersecurity lab, CTF, catch the flags, environments. Community-driven evolution. So everybody can work together. That's from the beginning of the invention Linux. As I said, it is written by 8 students. So with his friends, he built more and he released it to public, so anyone can contribute technically. Thousands of developers worldwide contribute. Bugs are fixed fast. Features evolve based on real need. One of the real need is that if Linux once Linux operating systems needs to be evolved to control more efficiently robotics, so that they developed ROS. R stands for sometimes real time. R stands for some other times called robotics operating systems. Linux as ROS. Cost efficiency without capacity loss. If you compare the size of the operating systems of Windows with the operating systems, the Linux, then Linux is lightweight, right? But capability is paramount. Foundations of modern computing, that is also possible in Linux. Okay, what is Linux? So if I click this, then that happens. So this is my trick. Copy the video URL and come back and paste it, run.
In this video, I go over what is Linux, why people use it, and what people use it for. So what is Linux? Well, it's a completely free operating system that runs on pretty much anything. And Windows, much like people think, hey, it's an operating system, it runs just on a select few PCs, where Linux is far more robust, compact, slim, lightweight. All these things are attributed to Linux, and that's why it runs on PCs, it runs on servers, it runs on smart TVs, it runs on set-top boxes, it runs in your phone. That's what is Linux. I mean, Linux it makes all those things run. It makes them go. It makes it to where those screens, all those devices can all talk together. It's basically a low-level software that sits and makes everything run. And that is what Linux is, and I'll get into where it comes from. So while all that sounds great, where did it come from? What was its origin? Well, it was based on Unix, which I've already kind of said, but Unix was created by Bell Laboratories in 1969, and it stayed that way until the early 80s, where a guy named Linus Torvalds picked it up and said, hey, I want to create that, but I want it to be more for an academic space. I want it to be completely open and free. So he was the one to actually pick that torch up and basically the creator of Linux. And then he opened that up and started sharing it with other academics. And those guys basically just grabbed any piece of hardware they could find and just scavenged up everything from personal computers to little handhelds, just anything they could get their hands on that they could install the Linux kernel on. And they basically documented they were the early pioneers of Linux, and for good reason. I mean, this is just an amazing thing. And it really wasn't until 1991, I believe it was, where Linus was able to actually go and really start to collaborate with these guys and really pull together a big team to really release the first version of Linux. And 2 years after this was done in 1993, Linux already had over 12,000 users. That's kind of amazing because of just the amount of growth. And also, you got to remember, back then, I mean, it was just Mac and Windows. And hell, I mean, I guess today you could honestly say it's just Mac and Windows, and Linux is kind of an afterthought in the desktop computer space. But you fast forward to today, and it's almost in every single server environment. Hell, it is in every single server environment. There's not practically any place I can think of that doesn't have Linux as far as data centers go. So for data centers, when I say almost everything uses it, You got web servers, almost 90% or more web servers use Linux. You have all your smart TVs pretty much use Linux nowadays. And Android is actually a modified Linux kernel, but you can debate this, but it actually uses Linux. So more than half the phones or smartphones in the world use Linux. It's a bit of a bold statement, but there's some truth to that. And I just kind of wanted to say this is its origin story. This is where it's at. And where it could really expand or really improve on is actually desktop adoption, desktop environment adoption. And that's kind of why I made this channel, because I love Linux. It's a great operating system. Fantastic. All these other places use it. And I made a separate video, and I'll go ahead and tag it up there. And that basically explains why people don't use it, or why it isn't widely used in today's desktop world. But that is Linux's origin. So let's get into why people are using Linux, and it's everywhere, but it's extremely prevalent in the server world or the data center world. And I wanted to kind of get in that and touch on to the main points of why you see it on there, and you also see it on smart TVs. You see it on a lot of different devices out there. The first thing I want to say about Linux is it's very, very stable. And when I say very stable, I mean there's screenshots of system admins that had a Linux box up for 10 years. 10 years without it even rebooting. That's a whole decade. That's amazing. Now, mind you, I think he was running offline with that, and it was running like an elevator system or something, because I think all the comments were like, hey, you're going to get hacked. You haven't updated the security of that kernel in 10 years. But that's another point altogether. It's amazing. It can run for 10 years straight, and it has, and people have screenshots of that. And that is just a phenomenon in itself. So the second point is it runs on anything, and I do mean anything. We have an old laptop that's almost, I think it's 8 or 9 years. No, it's 10 years. It's 2008 when I bought that. It's a decade old itself, and I went ahead and loaded Linux on it because I think it was running Windows 7 at the time. And it started really bogging down like Windows does. And I put Fedora on it, and I think it's running Fedora 27, so I need to upgrade that. But my wife uses it daily, and she loves it. It's still running great. So if you have an old laptop, repurpose it. Put Linux on it. There's no reason to have like an old version of Windows on anything anymore. It just doesn't really do anything for you other than just headache and heartache. And the third reason why so many people use it is it's secure. It's very, very secure. If you install CentOS or Red Hat, it has security enhanced Linux, which is even more secure than the base Linux. And you can put a whole range of things. This is one of the big reasons why a lot of web hosts and things of that nature use Linux, because there's a lot less of a chance of a hack happening unless they didn't properly update like a PHP module or something of that nature and someone exploited it. But I don't want to get too much into that. I just want to say it's far more secure than Windows, because Windows is closed source. We don't know what that source code is, and a lot of exploits are just there because there is no peer review. There's nobody out there looking at Windows code except for Microsoft. And if Microsoft finds something, they may or may not tell the public. Or they might just tell like the NSA and say, hey, I got this exploit, or the NSA might request a backdoor from Microsoft, which has happened, to get into Windows. So that's a big problem, and something Linux doesn't have. It's extremely secure. Governments can approach Linux and say, hey, we need a backdoor to snoop on people. That's pretty cool that Linux is open source and it has peer review, so that doesn't happen. And the final point, and it's a big one, it's free. So just to give it a perspective of how much money a business can spend on a server, or entire just licenses for Windows Server. I remember probably in, just a couple years ago, buying a bunch of Server 2016 licenses, and you can drop 10, 20K just on a handful of servers. That's insane. And just imagine you have racks and racks of servers. You can easily blow through $250,000 to $1 million. And if Linux can accomplish the same thing and be free and do it better, more secure, reliable, which one are you going to use? So that's why you see a lot more Linux in data centers. That's why you see Microsoft starting to come into the Linux community, because it's starting to turn heads. Almost every data center is really heavy on virtualization, except for Hyper-V. Pretty much Zen Server and VMware both use a Linux-based hypervisor. So that's pretty powerful. I mean, that's really powerful. And that is why people are using it, and why it's such a fantastic operating system. But I wanted to just kind of make this video as an overview for newcomers that are like, hey, I want to try out Linux, I want to do it. And as a system admin of 15 plus years, I wanted to just give my take on this question of what is Linux, why people use it, and just why it's so awesome. Thanks for watching my video. If you have any feedback or comments, please let me know below.
Next. This video explores how Linux runs on a wide range of embedded platforms, from tiny devices, could be your cell phone, or your smartwatch, to powerful edge systems, maybe anything that you want to implement a reliable way, then where there is a Linux operating system runs, forming the software foundations for connected and autonomous applications. So copy this right here, paste and run.
When most people hear the word Linux, their mind immediately jumps to a desktop computer, maybe a laptop running Ubuntu, Fedora, or some hacker-style terminal full of green text. But here's the twist that almost nobody talks about enough. The desktop is actually one of the least important places Linux exists. Long before Linux became an alternative to Windows or Mac OS, and long after desktop market share arguments stopped mattering, Linux quietly took over the world in a much deeper way. It slipped inside tiny devices, invisible systems, and everyday objects that don't even look like computers. And today, if you look beyond the desktop, Linux is not just present in IoT and embedded systems. It is the backbone holding the entire ecosystem together. To understand why Linux dominates IoT and embedded systems, you first have to rethink what a computer really is. A computer is not just a screen, keyboard, and mouse. A computer is any device that takes input, processes it, and produces output. By that definition, your Wi-Fi router is a computer. Your smart TV is a computer. The control unit inside a washing machine is a computer. Even traffic lights, elevators, medical devices, industrial robots, drones, and smart meters are all computers. Most of them don't have a desktop, don't run apps in the traditional sense, and don't care about user interfaces. What they need is reliability, efficiency, flexibility, and control. And this is where Linux shines in ways no desktop operating system ever could. Linux was designed from the beginning to be modular. You can strip it down to the bare minimum or build it up into something massive. This flexibility is almost impossible to overstate. In the desktop world, you install Linux and get thousands of packages whether you want them or not. In embedded systems, you can build a Linux system that boots in a few seconds, uses only a few megabytes of memory, and does exactly one job for years without crashing. This is not an accident. Linux gives engineers full control over the kernel, drivers, system services, and user space. Nothing is forced, everything is optional, and that freedom is gold in embedded development. Another reason Linux fits IoT so perfectly is hardware diversity. Embedded systems don't run on standard PC hardware. They run on ARM chips, RISC-V processors, custom system-on-chips, and specialized microprocessors designed for very specific tasks. Linux supports an enormous range of architectures. From tiny single-board computers to powerful industrial controllers, Linux can be compiled and tuned to match the exact hardware requirements. Vendors can add their own drivers, optimize performance, and still rely on a mature, battle-tested kernel instead of reinventing an operating system from scratch. Cost also plays a massive role. In IoT and embedded systems, margins are often razor-thin. When you're producing millions of devices, even a small licensing fee can become a deal breaker. Linux is open source, royalty free, and backed by a global community. Companies can use it, modify it, and ship it without paying per device fees. This alone makes Linux extremely attractive compared to proprietary real-time operating systems or closed embedded platforms. But it's not just about saving money. Open source also means transparency, and in a world where security is everything, transparency matters more than ever. Security in IoT is one of the biggest challenges of our time. These devices often live in the real world, connected to networks, collecting data, and sometimes controlling physical processes. A vulnerability in a smart lock or a medical device is not just a software bug, it's a real-world risk. Linux benefits from decades of security research, constant updates, and a massive community reviewing code. While Linux is not magically immune to vulnerabilities, the open development model allows issues to be found, patched, and audited far more effectively than in closed systems. For embedded developers, this means they can build secure systems without starting from zero. One of the most misunderstood aspects of Linux in embedded systems is performance. There is a common myth that Linux is too heavy, too slow, or too complex for small devices. That might have been true decades ago, but modern embedded Linux is incredibly efficient. Developers can configure the kernel to include only what is necessary. No graphical stack if you don't need it. No unnecessary drivers. No background services eating resources. The result is a lean, fast, and predictable system that can run comfortably on limited hardware. In many cases, Linux performs better than proprietary alternatives because it can be tuned so precisely. IoT devices also need networking, and this is another area where Linux completely dominates. Networking is built into Linux at a fundamental level. TCP, IP, Wi-Fi, Bluetooth, Ethernet, cellular connectivity, VPNs, firewalls, and advanced routing are all first-class citizens in the Linux ecosystem. For IoT devices that need to communicate securely and reliably, Linux provides a mature and flexible networking stack that has been proven at internet scale. This is the same networking foundation that powers servers, cloud infrastructure, and data centers around the world. Using Linux in IoT means tapping into that same robustness. Then there's the development ecosystem. Writing software for embedded systems used to be painful. Tool chains were limited, debugging was difficult, and documentation was often locked behind paywalls. Linux changed all of that. Today, embedded Linux developers have access to powerful build systems, debuggers, emulators, and testing frameworks. Projects like Yocto, Buildroot, and OpenWrt allow developers to create custom Linux distributions tailored to specific devices. These tools handle everything from kernel configuration to package management, making it possible to build repeatable, maintainable systems at scale. Linux also plays extremely well with modern development practices. Continuous integration, automated testing, containerization, and remote updates are all easier when your device runs Linux. This is especially important for IoT, where devices are often deployed in the field for years. Being able to push updates, patch security vulnerabilities, and add features remotely is not optional anymore. Linux supports over-the-air updates, rollback mechanisms, and version control in ways that are difficult to replicate with simpler operating systems. This makes Linux-based IoT devices more resilient and One of the most fascinating aspects of Linux and embedded systems is how invisible it is. Most users have no idea they are interacting with Linux every day. When you turn on your smart TV, Linux is likely booting in the background. When your router manages your home network, Linux is routing packets silently. When a factory robot moves with precision, Linux may be scheduling real-time tasks behind the scenes. This invisibility is actually a sign of success. The best embedded systems are the ones you never think about, and Linux excels at getting out of the way and doing its job. Real-time performance is another area where Linux has evolved significantly. Traditional real-time operating systems were once considered superior for time-critical applications, but with real-time patches and careful configuration, Linux can now meet strict timing requirements. This has opened the door for Linux in automotive systems, industrial automation, robotics, and aerospace. Cars today are packed with embedded Linux systems controlling infotainment, navigation, driver assistance, and even core vehicle functions. The automotive industry's shift toward Linux-based platforms is a clear sign of trust in its capabilities. Scalability is yet another reason Linux dominates embedded systems. The same core operating system can run on a tiny IoT sensor and on a massive industrial controller. This allows companies to standardize their software stack across multiple products. Engineers can reuse code, tools, and knowledge, reducing development, time, and complexity. This kind of scalability is incredibly valuable in fast-moving markets where time to market can determine success or failure. Community support is often overlooked, but it's a huge factor. Linux is not maintained by a single company. It is supported by a global community of developers, hardware vendors, researchers, and enthusiasts. When an engineer encounters a problem, chances are someone else has already faced it and shared a solution. Documentation, forums, mailing lists, and open source projects create an ecosystem where knowledge is freely available. In embedded systems, where hardware quirks and edge cases are common, this collective wisdom is priceless. Another subtle but powerful advantage of Linux is longevity. Embedded devices often need to be supported for many years, sometimes decades. Proprietary operating systems can disappear, licenses can change, and vendors can drop support. Linux, on the other hand, has shown remarkable staying power. It has been around for over 3 decades and continues to evolve. Companies can maintain their own long-term support branches, apply patches as needed, and remain independent of vendor decisions. This level of control is critical in industries like healthcare, infrastructure, and defense. Energy efficiency is also crucial in IoT, especially for battery-powered devices. Linux allows fine-grained control over power management, CPU scaling, and peripheral usage. Developers can optimize power consumption at every level, from kernel scheduling to device drivers. While extremely tiny microcontrollers may use simpler operating systems or even bare metal code, Linux dominates the space where connectivity, processing power, and energy efficiency need to be balanced. It's also important to talk about innovation. Because Linux is open, it encourages experimentation. New protocols, new hardware platforms, and new ideas can be tested and deployed quickly. This is one of the reasons Linux is at the heart of emerging technologies like edge computing. As more processing moves closer to where data is generated, embedded Linux systems are becoming smarter and more capable. They are no longer just simple controllers. They are intelligent nodes making decisions in real time. The relationship between Linux, IoT, and the cloud is another key piece of the puzzle. Many IoT devices act as bridges between the physical world and cloud services. Linux provides a natural connection point. The same tools and technologies used in cloud servers can be adapted for embedded devices. This creates a unified ecosystem where data flows seamlessly from sensors to analytics platforms. Developers can use familiar programming languages, libraries, and frameworks across the entire stack, reducing friction and accelerating development. Critics sometimes argue that Linux is too complex for embedded systems. And yes, Linux does require expertise, but complexity is not the same as weakness. In fact, Linux's complexity is what makes it powerful. Embedded systems today are not simple. They require security, networking, updates, and integration with larger systems. Linux provides the tools to manage that complexity rather than hide it behind limitations. As we look to the future, the role of Linux in IoT and embedded systems is only going to grow. The rise of smart cities, autonomous vehicles, industrial automation, and connected healthcare will demand reliable, secure, and flexible platforms. Linux is already there, evolving alongside these trends. New architectures like RISC-V are gaining traction, and Linux support is expanding rapidly. This ensures that Linux will remain relevant no matter how hardware evolves. Beyond the desktop, Linux is not just an operating system, it is an infrastructure layer for the modern world. It runs quietly inside devices we depend on every day, making complex systems work reliably and efficiently. It empowers engineers to build solutions that scale, adapt, and endure. And while desktop debates will continue, the real story of Linux is being written in factories, homes, cities, and networks across the globe. So the next time you think about Linux, don't picture a desktop environment or a terminal window. Picture a smart sensor in a field, a router managing traffic, a car navigating a highway, or a robot assembling products with precision. That's where Linux truly lives. Not on the desktop, but everywhere else, shaping the invisible foundation of the connected world we're building right now.
Okay. Next video clip. Do this. All right. So let me try if it works. Oh, no.
Hello and welcome to the special edition of the App Dev Angle live from the Open Source Summit North America 2025. My name is Paul Nashwaty, covering the app dev space and all things open source. I'm joined today by Justin from Peridio. Justin, how you doing?
Oh, excellent. Thank you so much for having me.
Yeah, thanks for being on. Why don't you tell the audience a little bit about yourself, a little bit about the company?
Sure. So my name's Justin Schneck. Yeah, I'm Chief Product Officer here at Peridio. And we've been working for over 2 decades in the experience chain for embedded product design and development. I've seen it all for people building tiny consumer electronics, industrial automation, all the way through to consumer, to commercial events, and all of that nature. So tiny devices, that's my jam.
Oh, that's really cool. Really, I mean, I was trying to get on the keynote this morning, trying to win that Raspberry Pi. I was really excited about that. I didn't get it, unfortunately. But let's jump in. I mean, embedded Linux. What do you have to say about that?
Well, embedded Linux can be really hard. It presents challenges that we don't typically see a lot of in the case of just developing software for purely digital environments. One of the areas I like to talk about really is that the differences that the web has for software development. It's an environment that we've created ourselves as humans, and we really have deep control over that. Whereas in the embedded market, we're building products that go into the physical space, and that demands some guarantees that we don't get from the pure software digital domains. Sure. Things like cosmic rays could cause issues of flipping bits. There's so much that can happen that is the unexpected that you have to be able to be defensive in programming about. So.
Yeah, it sounds a little bit science fiction there, with solar rays and such. But yeah, that's really cool. So let's talk about. Well, let's jump into like your shirt. You have Avocado OS. Avocado OS. I think it's interesting. I like the brand. Tell us about Avocado OS.
Yeah, Avocado is a binary distribution that's made to be able to create AI native runtimes for companies who need to be building embedded products that in this modern age of edge AI can perform some really complex tasks to create the next generation of products quickly. And what we found is why there's a need for this is that there's this traditional dichotomy of choice that we see in the marketplace between something called Yocto, which is extremely high learning curve up front, but does set you up for success with what we need for those things in embedded products. Deterministic runtimes, immutability, reproducibility, and on the other side of things, we see things like desktop distributions. You have Ubuntu and Red Hat in those spaces, and those systems, they're very easy to get up and familiar experience for developers up front, but arguably aren't really scalable towards tens of thousands to millions of devices in the field. Avocado kind of threads the needle in the middle, and we create an experience that is really developer friendly. It gives you that feeling of package management, being a binary distribution, but not at runtime, at build time.
Okay.
And what this enables is that in traditional product development firms, you usually have this bottleneck that occurs between application developers who need to get their stuff onto devices to test, and systems integrators who operate at these slower development life cycles. And now with the advent of edge AI being a thing, in order for that to take off, we're introducing another party to the group, data scientists.
Okay.
And they need to be able to operate at an even faster pace, right?
Yeah, so, okay, this is really exciting, right? Because there's a new kind of reason you're doing this, right? You've explained the differentiation in the market, why you're doing it. It makes a lot of sense. And so, I know that you have a public beta coming out. Is that available now? Is that something that's coming out soon? What's the when can we get this?
Yeah, well, we came to the Open Source Summit to be able to actually give an official launch on that one
Very
here
cool.
today.
Yeah.
And we're coming out swinging with 3 platforms that we chose to start. We're working with the NVIDIA Jetson Orin series boards. We also are supporting the NXP IMX 93 series.
Okay.
And also for all those developers who happen to have maybe won one of those Raspberry Pis, the Raspberry Pi platform, just because it's ubiquitous.
I could have run Avocado on my Raspberry Pi that I didn't get.
That's right. Well, I'm sure that you might be able to have a friend who has 2 or 3 of them in a drawer somewhere.
That's
too.
perfect. I'll go find that. So, all right. Well, I think I have to touch on here NVIDIA, the NVIDIA relationship. I mean, that there's a lot of buzz in the market. NVIDIA is kind of obviously a hot industry darling out there today. So let's talk a little bit about the relationship there.
Yeah. So leading up to the summit, we've been wanting to put together a demo that was really compelling and captivating for the people in the audience, right? So we work closely with NVIDIA leading up to be able to illustrate and demonstrate how easy it is for those data scientists to quickly iterate on their devices. The Jetson series stuff is complicated. I mean, running Edge AI in itself is a complicated stack. And the demo that we put together with them is running this product that they have called Triton Inference Server that has some great benefits. It can do live model reloading in the fly. It can do model ensembling. And it provides a really nice development experience because together with our hardware-in-the-loop debugging technologies, then it allows these data science groups to be able to quickly see changes in their models and enumerate on them really quickly on the physical hardware instead of it being virtualized in a domain.
So we're going to see Jensen up there on stage with a Raspberry Pi running Avocado pretty soon?
Yeah, I hope so.
That'd be really cool.
Great.
Yeah, really awesome. Yeah, I look forward to seeing that. So okay, let's take a look at other manufacturers, top silicon manufacturers that are interested, right, in this whole approach.
Yeah. So as I mentioned, that dichotomy that we see of choice. So these top silicon manufacturers, these are the best that they have at offering to their customers. As I mentioned, Yocto being a steep learning curve, but desktop distributions being easy. They wanted something that's going to enable their customers to be able to move more quickly without sacrificing that ability to go to production. Usually we'll see if you get started on a prototype with something like Ubuntu, you're going to hit this moment where you need to productionize it.
Right.
And when you harden systems like that, you kind of put the seatbelts on and you make it difficult for developers to move quickly. The more you harden a system, the more difficult it is for them to iterate.
Sure. Yeah.
So we've been having a lot of conversations with some of these top manufacturers about this problem that they experience and how Avocado can really help offer a solution that doesn't have those compromises.
So who are some of those manufacturers? Can you share those names now, or is that still in kind of development?
It's still in progress.
That's
on
fine,
having some more of those conversations together, but every one of them is experiencing this kind of pain. And we see a lot of these example cases that are in the field of acquisitions that are happening for hardware companies because they know that they need to become more vertically integrated with software solutions so that they can sell more silicon and actually make the promise of edge AI start to take off in a sustainable way.
Yeah, I mean, I think that makes a lot of sense. I mean, there's definitely growth. When I think of my practice, I talk about past, present, and future, and I talk about moving from heritage environments to the next generation, which is modernized approaches using depending on whatever the location that you're at. So you can be in your core data center, you can be at an edge location, a cloud, wherever it may be. But when we think about the expansion of these applications, there's all sorts of workloads that are happening across the board, right? And there's also difficulty in kind of managing some of these workloads, right? So when we think about that from embedded devices, right, let's talk a little bit about the tooling around embedded devices. What are your thoughts around how Avocado OS can help with the tooling of the OSs?
Well, we think about things a little bit different. Well, actually, the inspiration comes from battle-tested and deployed opinions that come from things like systemd, like technology in the embedded Linux space, it's just Linux running smaller. And so the user group, the user space group from Linux, they've been doing a lot of work in service of making distribution installations for server and cloud architectures more hygienic. And by that I mean they were making it so that they can install multiple distributions alongside of each other and also make it so that they can clean up some of the legacy in the space.
Okay.
And so we are depending on a lot of these opinions that have been formed and tested from upstream cases and applying them to rethink the way that we structure embedded devices. Typically in embedded systems, we would build monolithic root file systems that would, you'd ping pong between an A/B system. So today your root file system with your machine learning models, you might be like, oh, it takes up 250 megabytes. And then tomorrow, so you lay out your partitions such that you give yourself maybe half a gig of space, right? Tomorrow your data scientist comes to you and goes, guess what? 1.5 gigabytes I need. Well, that can lead to a really problematic, risky repartitioning in the field. That's a one-way ticket. And that complication means that we have to be really knowledgeable and prepared up front. Avocado takes an approach where, using this technology from systemd called system extensions, we let you have an environment where you can introduce packages at build time, you can create an OS tree that acts as an overlay at runtime, and that overlays on top of our very thin, minimal root file systems, so that way your partitions can remain consistent, and all of the rest of the disk is your playground of a dynamic space that we format to let you build your extensions. Therefore, if that size increases or decreases, you still get all the guarantees that we need for determinism, runtime support for embedded devices, but you don't have to deal with that hard problem of repartitioning in the field.
Yeah, absolutely. I think that's you're overcoming some of the challenges that we currently see today, especially with heritage environments. I mean, I think it's you're overcoming those. So you mentioned a couple of things. I want to be kind of clarify. So I understand is the persona you're talking to. You mentioned data scientists, but you're talking very much like a developer-centric kind of view. Is it more of like the line of business developer, citizen developer as a data scientist, or is it a professional developer that would be your target?
Well, I mean, anybody who's wanting to be able to build a product, and really, in order for us to have this sustainable growth period for Edge AI to take off, we're going to need to get tools in people's hands so that they can have these innovative ideas come to life quickly.
Right.
I think back to the 2010 era where we started to hear about IoT, and all of the same complications of building embedded systems existed then, including ones around how do I even make user interfaces. Well, in this time, kiosks became a big thing. We started to see Chromeless web browsers enabling existing web development teams the power to feel like they can actually build embedded products quickly. Without having to have really low-level, experienced, Linux, low-level developer talent on board. We're going to see the same thing with Edge AI. I mentioned data scientists and average, generalized developers because it's going to take tools that let them feel capable to create products to spur that innovation spike and have it so that they can start to be able to bring their ideas to life as well.
So it's very cool. So I think and what I heard you say, just kind of translated into kind of simplicity views, is like it's bridging the old with the new, right? It's like it's basically taking your existing approach, and it sounds like there's a migration path here that can occur pretty seamlessly. Mm-hmm. Is that true?
Yeah, and the nice thing is that since we're leveraging a lot of tools and opinions, but redesigning using those the way that we approach the composition of an embedded system, we're not really introducing a lot of new code. And so, we're taking battle-tested ideas that happened in the cloud, but we're adapting them with the right approach for embedded development. And that means that we're getting production-level grade results from day zero without having to wait a long period of time because we might be doing things off the beaten path.
Sure. Sorry, let me ask you a question, Justin. So a year from now, when we're sitting here at Open Source Summit, where do you want the company to be?
Well, I would love to be able to see more people kicking the tires on this and having a nice growth period. We're getting a lot of great feedback from developers here at the conference. It's been a fantastic event to be able to see how they're receiving it.
Yeah.
And I would think in a year from now, it would be great to have the community start to flourish and grow and have more people being able to build products using this this platform and this design pattern. And so I just truly want to be able to see what people can do.
Yeah.
I want to see the products. I want them to exist. And I think that enabling this is going to let them create the stuff that I just want to have the joy of playing with myself.
Of course,
right?
that's awesome. That's awesome. Well, I'm super excited about your success so far. I'm really excited to see where it's going in the future. So that's awesome, Justin. Thank you for being here. Your insights have been awesome. I'm really excited about seeing where it's going. And thank you to the audience for tuning in. We really appreciate you being part of the AppDevAngle community. That wraps up this episode, but we'll be back next Wednesday.
Okay, so avocado, like apple. Like apple better than avocado, or avocado better than apple? I'm excited. I mean, this is a really interesting idea. Okay, I wrote here, recorded live on Open Source Summit North America 2025, Paul Nashawati, principal analysis of the Cube research, sits down with Justin Schneck, chief product officer at Perio, to discuss Avocado OS, a modern and developer-friendly distribution of embedded systems and Edge AI. Interesting things in addition to the mainstreams of OS. So Linux embedded AI robotics, modern humanoid robot platform integrates a high-performance embedded CPU, GPU. Both are running on Linux. So AI perception and decision-making, real-time control loops, motion planning and sensor fusions, and robotics middlewares, ROS, RS2 on Linux. So our ROS, as you see some of the previous video clips, they said real-time operating systems. But here, those who are working on robotics, they call it robotics operating systems. Okay, so robotics is becoming very, very popular and powerful, particularly in this year. If you see SEC 2026 already held in Las Vegas, I think January 4 to January 10th, somewhere there, right? So robotics, where there is a Linux running on the line. So Linux is a de facto OS for robotics software stacks in both research and applied domains. So some of the top 10 humanoid robots explained in this video clips. This is not the current. This is a few months old. But you can see, oh, that was a few months old. Then how much it could be evolved? Very much. I mean, exponentially. So robotics are already deployed in manufacturing companies. So that type of thing is possible. So why don't we look at some of those?
I believe it's inevitable that humanoid robots will get involved with construction in a meaningful way over the next decade, maybe even sooner. The technology is still early, but I've put together the top 10 humanoid robot demonstrations in anticipation of the day humanoid robots start taking meaningful roles on construction sites. Many of the tasks we'll see in these demonstrations today are not related to construction, but like everything else, with technology, we'll see it advance one step at a time. Here's the Eve robot from 1X, with their founder passing on a 40-pound bag of rice to the 70-pound robot, which it's able to hold and navigate with relative ease. This robot uses soft touch so that it doesn't hurt people, even though it's able to hold heavy loads. By coincidence, bags of concrete are also often 40 pounds, sometimes even lighter. So it's easy to imagine how this could be applicable on a job site, even though the robots probably aren't ready for the dirty dust that comes with concrete yet today. Now on to one of the most prolific humanoid robot companies, Figure. Founded by Brett Adcock, this multi-billion-dollar startup has launched their third generation of the Figure robot, and they're demonstrating here the folding of a towel. For many years, people said robots folding laundry was impossible, and we're seeing that be proven wrong in real time. Now it's just a towel, and some of the movements look a little bit awkward, but it's only getting better from here. Back in the day, chess masters used to say computers would never beat a human at chess, and then they said they would never beat a human at Go, a more complicated game with far more potential moves. Both of these predictions were proven drastically wrong. Not only are the computer softwares like Stockfish capable of beating the most advanced chess experts in the world, people are also learning new moves and strategies from these computers, which generally train on a series of simulations, often playing against itself in a massive number of games that are only possible to simulate with computers. These simulations are similar to the way people are training humanoid robots today, primarily through two different methods. The first being video footage of humans completing the task, often with cameras on their bodies located in the same place the robot has its own cameras. The other method is virtual simulation, where they have the robot operating in a digital emulator and they have it complete the task X amount of times, many more than you'd be able to complete in the real world because you don't have the same time constraint. You can operate 2,000 different samples at once and then train the real robot based off the results of those digital tests. One of the biggest contemporary challenges with humanoid robots is hand dexterity. You can see they don't necessarily have the same pliability or mobility as human hands do, but they're improving with every generation of the robot. I find it fascinating how, even though every towel looks identical, the way they lay on the table once they're pulled out is unique in each circumstance, yet the robot is able to achieve a more or less uniform square from each one. One task at a time, the people saying humanoid robots can never do that will be proven wrong, just like the naysayers of Thomas Edison were proven wrong, when light bulbs took over candles and gas lamps to become ubiquitous in modern day society. Here's the Tesla Optimus Bot. It's an older model. Elon recently announced the Gen 3 will be released soon, which is planned for mass production. They hope to achieve thousands of units this year, scaling up 5 to 10 times every year for the next few years until there's millions, maybe billions, of robots like this around the world. Elon is known for making lofty claims, and they don't always come true on time, but typically they do come true eventually. This is the K-Bot from K-Scale Labs based in Palo Alto. It's an open source humanoid robot, and they're developing both hardware and software for developers to be able to program the robot to complete new tasks. This is a 4'7" robot that weighs 77 pounds, and it's available for a $100 pre-order fee. Ultimately, they expect the price to be $9,000, making it one of the more accessible humanoid robots. It'll be exciting to see what the open source community does with this. Plus, it has a cool Rage Against the Machine style TV head. This is the AGI Bot X2N out of China. It's got a really cool feature I've never seen before. There's a big debate in the humanoid robots world of whether it's more practical to have feet or wheels. This company thought you shouldn't have to choose. It's a shorter robot, but you can see in this flat landscape, it's wheeling around. Then once it reaches an obstacle like stairs, which requires steps and standing, it converts those same wheels into feet, which are then able to both walk on the flat surface and navigate up the stairs. It's fascinating watching the robot step, misstep, recalibrate in real time and not fall over, and then transition right back into the wheels to go down the ramp. The real world has all kinds of complicated obstacles, so it's imperative a humanoid robot would be able to navigate them without falling or tripping over, especially if they're holding something important. It's awesome seeing companies like this thinking outside the box and bounds that other companies are considering, like the choice between wheels or legs. I find that seamless switch super impressive. I can only imagine it's more energy efficient than walking to be rolling around on wheels. I see humanoid robots like the missing link or the fish that walked onto land. It's not the most practical thing for the job, but it's the step in the direction we need to automate the future. Here's a company called Skilled AI. What's unique about this situation is the robot has never encountered it before. They have one model, and it's using that model to navigate this fairly complex situation with many challenges, including rolling around, unstable pallets, uneven surfaces, and it's managing to go through all of them. Although it trips and fumbles sometimes, it doesn't fall, and it continues down the
That
path.
humanoid robot's
While we
better
watch
than
this humanoid robot navigate a variety of
We need the
surfaces,
wheels.
let's talk about one of the other major challenges currently facing the humanoid robot industry. It's the actuators in the legs and the arms. They have a tendency of overheating. Most companies are realizing they'll have to develop their own actuators in-house to reach their goals, as the requirements are not readily available from overseas suppliers or even US-based companies. In most big cities today, you can see a variety of robots, whether it's self-driving cars or tiny little boxes doing mobile deliveries. Sometimes people treat them better than other times, but I'm wondering, how would you react if you saw a robot like this carrying a package down the street? I think most people have less empathy for robots than they do for other people, and that's only fair. It even feels awkward for me using the word empathy to describe the way you treat a robot. That said, there's situations where people don't have empathy for each other anyway. Things get stolen, people get assaulted, and the same thing will happen to humanoid robots on occasion. A big difference will be the humanoid robots are likely to be outfitted with cameras, so it may be a little bit harder to get away with. There's always going to be Luddites and technology haters, but in this day and age, we've pretty much all fully embraced it, carrying around a computer in our pockets everywhere we go, to the point where, oftentimes, if we leave our phones behind, we get missing limb syndrome, and may even feel phantom vibrations from a phone that's not even actually onto the Walker 2 from UB Tech. They seem to be demonstrating at this conference in a simulated factory setting where the robots are completing a variety of tasks that would be necessary in either a toy production factory or many other types of factory environments or warehouses. A great feature of this system is that it's able to replace its battery on its own, removing the need for a human to plug it in or place the battery for it. This humanoid robot is downright creepy. They tried to make an anatomically correct simulation of a human with myofibers and over 200 sensors. You can see the way it kind of moves around. It's strange being hung up like that, but they're trying to accurately simulate the muscle and tendon movement of an actual person. What do you think of this strategy? I'll tell you what, if I saw that through my neighbor's window, I'm probably calling the police. All jokes aside, there's probably some practicality to accurately simulating human movements if they're able to do so successfully. Everything in the world was designed for humans to be able to work with and use, so it's kind of the core thesis of humanoid robots that they would be the ideal form to automate many tasks people are doing today. While some companies like the robot on wheels that could switch to steps as needed are thinking about improvements to the human form, other companies like Clone are trying to copy it as closely as possible. This is my favorite demo of the year from humanoid robots because it's so related to construction. This is Torobo from Tokyo Robotics. It's demonstrating the ability to saw this piece of wood. Notably, it's not holding a saw. The saw is directly mounted to the arm of the robot. I would imagine it can do a more precise cut than a person could. It's also capable of hammering in this nail with a similar attachment rather than a hand holding the hammer itself. Conclusions are a personal weakness of mine, but if you enjoyed this video, check out my other video about the top humanoid robot companies, where I tried to list as many as possible. Some of the companies featured today are brand new, and now there's too many to count. But these were the best demonstrations I could find for you, so if you enjoyed, leave a like and subscribe. I believe it's inevitable that humanoid...
So what do you think about the robots?
The future.
And current.
And current, yeah. We're getting closer to the Jetsons.
Yeah.
The robot made.
Elon Musk will provide us, I think, $10,000 robots. Do you guys really need the robots in your daily life? Not me.
We don't know yet. Because they're probably going to allow us to do more.
Yeah, it depends on the types of the work that you should accomplish daily. But in my life, I don't. But if you're running, for example, a restaurant, cook, and that cook types of food requires lots of the heat. Think about in summer. it is almost even chef cannot sustain in the kitchen longer enough to serve if they have big customers, likely in winter as well, for any the cold stuffs that you have to deal with. From that environment to the war zone, real war. So we may be able to see maybe in the near future, maybe in Gulf, I mean the Middle East area, Iran. So who knows what types of weapons or robots where there is a Linux operating systems running. So think about their Linux operating systems if something is evolved sooner or later. So next one. So this is a little bit of the summary. So Linux provides a stable, real-time capable foundations for robotics control systems. ROS, ROS2 ecosystems rely heavily on embedded Linux distributions. So one of the embedded Linux is the Linux embedded on your Raspberry Pi microcontrollers. AI perceptions, vision, speech, sensor fusions. By the way, your Raspberry Pi has some of the ports that you can have. You can install the cameras. Okay, not your real camera, but there's a real cameras, but camera that is handled and controlled by your program. You can program on your Raspberry Pi, and that program can control your Raspberry Pi. I mean the cameras, so that your Raspberry Pi can have visions. Speech possible, and lots of sensors can be plugged into your Raspberry Pi. Although we don't do that in this class, but I can show to you. There are 40 pins available, so you can wire between your sensor and Raspberry Pi, and your program identifies those pins and control eventually the sensors. Open source drivers enable rapid integration of camera, that is movie cameras and still cameras, and LiDAR. As I said, the LiDAR is a two-dimensional regions identifications. Two-dimensional, it's not one spot. IMUs and actuators. In response to the data acquired from sensors, there may be some actions to be taken. That actions can be manipulated by actuator. Usually what actuator will do is from your Raspberry Pi, from whatever the program that you do, well, I have one of the demo that I implemented. I may show it to you. It has a usually it runs a motor. So motor runs, right? It spins. From there, from that motor spins, you can convert that circular movement into directional movements. That type of modulator, small piece of electronic devices can work for that. Okay, the last bullet there, there's a containerization. as Nicole responded earlier today, there's the well-known containerization is a Docker. I have a slide in the later on this lecture notes. If we have time, then we can take a look. Probably we cannot take a look all of those Docker introductions, but Docker is very handy and good, and also powerful. When you are involved in some of the developments using Linux, then you may be able to use Docker. Yeah, allows modular AI pipelines on robots. So Linux basic for robotics. The real Linux fundamentals applied to robotics development, geared toward the people getting into RS and AI robotics workflow. This is the slide. This is the video. Let's see if it works here. Oh, good.
Hello everyone, welcome back to our YouTube channel Becoming a REST Developer. I'm Desire, and today I've got Bono, who has just completed the course Linux Basics for Robotics, and he'll be giving us a presentation on that. So without any further ado, let me hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Bono.
Yes, sir. We will start with by running the obstacle avoider program in the real robot. The robot interface, and then.
Alright, can you adjust your screen so that you can see what the robot is doing? I think it's behind the wall there. Okay.
In the terminal, you can see that the robot are doing calculate of front range. Front range. You decide if you need to turn right or turn to left, moving forward. So, in the alpaca avoider program, the distance that the robot has to move, we do first of all the robot begin by scan the distance that is within the obstacle minus the threshold. So the robot has to move once. So after a new scan of the range, the robot will turn right or turn left. But in the simulation or and in the real robot, the robot moves twice, moving forward twice. I don't know why
But does it show you that it's calculating the next distance when it stops, or it just stops?
Just stop.
So that is in simulation, right?
That in the real robot.
Okay.
And also in the simulation.
Okay. All right. So right now it seems to be doing fine. I can see that it stops here and there, but maybe that's on the basis of how you are calculating the time to move, right? So from your saying, you said you calculate the time to move by subtracting the threshold from the distance to the furthest obstacle, right, in the front.
Yes.
Okay.
So is that good?
Yeah, it's let's leave it running so that it encounters more obstacles and hopefully avoid them, right? What I want you to do though is to explain to me what you did. How did you manage to get this behavior out of the robot? So let's open the obstacle avoider script and have it on the side, preferably on the right. Yes, and then you can explain to me how you managed to get that behavior. No, don't close the other side, because I also want to see what the robot is doing as you do that. Right, so maybe just leave one panel open. Right, and then you can, yeah, that's good enough. Now explain to me how you managed to get that behavior, and maybe show us where you're setting the parameters and then calculating the distance to move. I want to see that part because you made a mention to that, which means there is some detail there that you think is worth explaining.
Okay. At the beginning, I use the program in the Simple Patrol. That program.
The one you're given, yes.
Yes, that program helped me, and the comment, the comment in green, that helped me also. And I found another problem. For example, at the beginning, we have the Shiben, and here is the here is the way to find the robot function, because in the robot function file we have all the function that they get, scan, left, well range, all the function that we use, that the robot use to know the distance, front range, front left.
Okay.
I changed this this way because my robot function was in another where in another file.
Okay.
So I have to move to change the way
to change the
find
path.
the robot function.
Okay.
After that, we use echo to we have to use echo to see in the
Let me
terminal.
jump up a little bit.
But let's go on.
In that program, we have 8 keys.
You have had to have tried, or you just found that that's there? Did you try any other case where you had the robot rotate in one direction, it worked or didn't work?
So you what line?
Put a bit more thought into figuring out that, okay, I may have things in front of me, but that doesn't mean I should always turn right? What if there's something on the right? So what other algorithms normally do would set
Direction. You get Udon direction. Because it was we are telling that in the project
okay.
that to have the distance coverage things that we use to insert
So to
the
insert is to
program
right? So let's say you've
insert the program
done the
I use.
writing as always, and now you want to leave this editing.
Now I use I to insert. So to exit I use escape, and then I think this.
I think you're on the right track. You're just using the wrong letters.
I forgot.
Alright, it's colon Q, right? But you're using W. Do you know what does W do in the first place? If you use colon W like that, what does it do?
So I don't know.
Alright, you can go do some homework. It's in the course.
Okay, let's move. Okay, wait a minute. This is a student robot presentation. Okay, so let's take a look at this. Student robot part. Sang-Don Lee will do a presentation of the real robot project built during his completion of Linux for Robots course. So it's not working.
Hi everyone, welcome back to our YouTube channel. I'm Desire, and today we've got Sang-Don Lee.
Why there is no images? Only audio? This is an interesting project, student project, using Linux shell scriptings and also Python. So I want to show this to you, but not possible. This.
Hi everyone, welcome back to our YouTube channel. I'm Desire, and today we've got Sang-Don Lee, who has just completed the course Linux Basics. So he'll be giving us a presentation on that. So first of all, as we always require,
Let me get it from here. To see.
and finally the obstacle avoider.bash. So pretty much, I tried to play with the threshold. I didn't change it.
On that. So first of all, as we always require, we want him to show a demonstration of the real robot, and then after that, we can get into the details about what he did, how he did his project. So without any further ado, let me hand over the platform to him so he can begin his presentation. All right, whenever you're ready, Asengan.
Okay. So I'll have all these things implemented in the terminals interface first because we want to get it ready, the subscribers and the publishers, for the different things like the linear, angular, all the information that we need for the robot, and the function that we created to avoid obstacles. We do that. Okay, that looks good. And the statistics, print out the. Oh, I guess it's a copy. Let's see. Okay, there we go. And this is a project that I created. So pretty much this is the interface that we use all the informations from this, and then there's the functions where we get and set all the parameters that we get from the robot interface, and finally the obstacle avoider.bash. So pretty much I tried to play with the threshold. I didn't change it. I didn't want to be risky, so I used the default threshold that you guys gave me. And since we have to use scan ranges to detect obstacles, I get that from the getters that we set up from the functions that we created before. And then I created my own thing I want to be specific for the angles for different situations. So this is pretty much, I'll explain that later, but when left or right is blocked, when the front is not blocked, I'll try to command the robot to turn softly. And then when everything is blocked, then I try to say, turn sharp, so we have more space.
Okay.
And then it's a 0.5, sleep 2.3 seconds. It'll go for, so this is the duration times the speed. It gives us the radians, but I'm gonna have to change it to degrees. So I pretty much use the calculators, or I Google to see how much degrees it's gonna turn. And right is negative because if you turn clockwise, it's negative on the circle thing that we learned in high school, or pretty much. So that's why it's negative for right. So it might be confusing for some people. And
clockwise would be negative, so counterclockwise positive. So can we see this running on the robot first, and then we can speak about it later?
I guess it has to wait all the statements. It's a little bit slow, but it's not perfect. But
I think the most important thing is for it to at least to not crash, right? We want it to avoid obstacles. So it looks like it's doing that well so far.
So do you want me to go back to explaining the codes, or?
Let's wait for it to do a couple of more obstacle avoidance maneuvers, and then we can move to that one later.
Yeah, sure, sounds good. Also, like to, I guess, if you want to be closer to the obstacle, you can decrease the threshold.
Okay. Did you play around with it at some point to reduce it, maybe?
But I played around with it. Sometimes it just ran into the wall, so I just like, oh yeah, let's try to be safe, even though it might turn multiple times. As long as it doesn't hit the obstacles, it's doing its thing.
Yeah.
So I pretty much like set it back to the default. So I thought there's a reason why you guys set the threshold as 0.3.
Yes.
So I didn't try. I just like went back to normal threshold.
I saw it just reversed there. What happened? Did you do an implementation of that maneuver? And
Going back.
yes.
So I didn't want to turn like multiple times. So as you can see, it takes a lot of time for it to, turn to have like wait for the command. So I just said go back negative 0.1 for 1 seconds and then turn. So we have, it's quicker.
So
We have more space when we turn.
okay, I see. So are you saying the threshold, it exceeds the threshold at some point? Like, does it go beyond 0.3? Does it get too close to the wall in some instances? Or it's just a safety
For my
precaution?
code?
Yes.
Oh no, it's I'll show you. Oh no. Here we go.
All right. Because I want to know, like, what's the criteria for reversing, right? I thought 0.3
No,
was
I
good
think
enough for it to rotate. Yeah,
no, it's this case. So when it's the front is blocked,
Yeah.
so instead of turning, I just said I guess it's negative 0.15, negative 0.15, and just back up and just do the turns again. Just only for this case.
Okay.
It's backing up.
Okay, can you take me through the logic for why only for that case?
Well, it's because we have a lot of elif statements. It's pretty much like handling all the cases when left is not free or right is not free or just one of them is not free or both of them is not free. So based on this, you can see that right is free. So we just turn soft and we have non-free. Then we compare. We compare how much time we have moved. We have to use this distance because we already set up the variables up here for the different ranges like left, front, and front right, and right range. And we get the distance to move, and we minus the threshold, so we know how much distance we had before we hit the threshold. And then since we are moving at 0.1, actually you should change that to 0.15 if you want to be specific here. But you saying that we want to move 0.1 meters since that's what we set up as a linear speed, and you divide that to see how many seconds we want to move. And the seconds we want to move is as long as it's bigger than 0, we know that we have time to move. So we set that up to 0.1.
Yes.
And we give its duration, so how long it's gonna move. So it moves its distance is time, time multiplied speed. So it gives distance, and we wanna stop it because otherwise it's gonna keep going. And then else is to close. If it's to close, then we just skip the forward motion, and we finish the statement right here. And it's a different logic for different cases. For instance, this is when it's not free for the left, and if front is free, front right is free, then we will turn. But sometimes you have to like the robot could be at different angles, so you can't really have one case to say turn this angle at this point, even though you have that based on the angle of the robot current position, it might turn differently, and sometimes it turns twice. And I was just being lazy, so I just didn't want a robot to turn twice. I just wanted the robot to go back once and then just turn, so we have more space in the front.
Okay, so you wanted to like be sure that you are clear of whatever obstacle it is.
Yeah, definitely.
Then
because I didn't want to wait.
And when it reverses, right? How did you choose the distance that it has to go for? Because I see it almost crashed into the wall, but it stopped, right? Are you also taking in consideration the laser scan data for the for the back of the robot? Are you considering those for obstacle avoidance as well to make sure that when it traverses, it doesn't hit an obstacle? Or you?
Sure. So I should have thought about that. I should have added the back ranges. So when I had that logic, when it's like less, the way you apply the same formula for distance to move, time to move, just make sure it stops when it reaches that point. I should have added that. But I based off the distance I chose was, when it goes to front or when I tested, it doesn't really like exceed a lot. But I guess what you're saying is when it's at like the middle right here, when it's I don't even know what that is, like a stone thing, it might crash into it.
Yes, it
So
might crash into it when it traverses. Yes, that's
yeah,
why I'm asking.
so I should definitely add that logic for the back range. I should have I don't know why I thought of that, but yeah, I should add the distance to move logic so you make sure it's safe when it backs off.
Yeah, yeah. Well, it will make your program a little bit more complex, right? But after you've
True.
implemented the reverse maneuver, I think it is important to take note of that as well, right? Because you will have cases where it reverses into an obstacle if you don't do a handling of that, right? So
True.
yeah, but
So I think does it have the back back range? Oh, they don't have that. It's pretty much just calling so I don't know why I had an error, so I looked up. I mean you guys have print $4 for everything, but I wanted to know how much sleep all this matters. Like
how did you get to the 2.3 value? Did you have to test?
yeah, so uh I pretty much what I did was like I told you I did a calculation of turning this to degrees.
Okay,
So I calculate the degrees. I believe this is like it's not that it should be below 60 degrees
okay.
and this should be over 60 degrees.
Uh-huh.
And I just based on the position of the robot, let's say if it's gonna be a little bit slanted when it's left is not free.
Mm-hmm.
So I just said we want to go like 45 to 60 degrees range before it turns too much. So
Right.
I chose, and then when we are too close to the wall, we want to turn way more. So I did to the 60 to 70 degrees. So that's why I chose the 60 degrees range for the turn right sharp.
Uh-huh. Okay. All right. All right. Very, very well done. Very well done on that. Okay. Thank you so much, Sangdon, for your presentation. So, I think we can.
What do you think about this student project? Doable? Doable, right? In another class, we have a graduate class that also uses Raspberry Pi, but we add sensors and actuators. Not really that moving vehicle robots, but it is kind of a robot also, because some actions can be taken in response to some situation changes, updates. So it's more like adaptive robotics. Of course, under that project, the Linux running. So video clips that we looked at so far, some of the basics and some of the applications. So when you do, if you in your career, if you are involved in some developments and also deployments of your products, then whatever you develop, most cases, I think 99.999%, your work is not just developed from scratch. You are adding on top of something already developed. So there is some dependencies, right? When you deploy your products, then it should be self-contained in one single system. You cannot say, hey, to run this, you have to have this kind of application needs to be installed first and properly configured. After that, you run this, which is not really a good idea, right? You have to gather all dependencies together in one container and deploy. That is the basic, that is the scenario that you need to do. That's what this guy would like to do, okay? Docker. In this semester, at this level, you are not going to do Docker, but I wanted to give you some of envisions, some of the challenges. You need to have, hey, this is, although I'm not at that age, but I have some dream, that dream may come true, or I will make it. I have some idea, although I don't get the concrete skill sets yet, but I have an idea. So I wanted to give some idea for that, okay? That's what I'm trying to do. And if it runs also here.
Hi everyone, hope you are having a good day. So imagine you are working on a web project, let's call it Retro UI. And to run Retro UI, you have some dependencies like Node, Python, Postgres. There could be many more, but for the sake of video, let's take these three as an example. And you are running that on your machine, which is running macOS. Now, let's say you got a new coworker and he runs Windows in his machine. To run Retro UI in his project, he also needs to install these packages, right? And most likely the same versions. Now, you two have been working on this project, everything is going good. Now it's time to ship for production. So you rented a VPS from some cloud provider, which is running Linux, and let's say it's running on a Ubuntu distro. To run Retro UI in this new Ubuntu machine, you need to install the same dependencies you had like in your desktop. So let's say for Ubuntu, you also install these Node, Python, and Postgres packages. So after you install all these dependencies, let's say for some reason Python version 1.20 is not very compatible with Ubuntu, or let's say you just mistakenly installed 3.11 instead of 1.2, which is not compatible with Retro UI. So Retro UI is properly not functioning in your web server. And that's how you might hear this term a lot in development world, that it works on my machine, because the environment of your machine is probably not the same in your client's machine or the server or the coworkers. You can see this is a very simplified example, but you can imagine as you get more and more employees with different OSs, or your project gets bigger and adds like new versions, like your server might need Nginx. So it gets very hard to like maintain all these environments, and that's where Docker comes in, where you take your environment and divide them into multiple containers. So for example, let's say for Retro UI, we divide all the dependencies into two containers. One is Retro UI frontend and another is Retro UI backend. And these containers are fully OS agnostic. So regardless if your coworker is running Windows or Linux or macOS, it should run perfectly fine in every environment. But if you haven't worked with Docker before, you probably have no idea what a container is and how they work. So stick till the end of the video, as I will share every major topics you need to know to work with Docker. It all starts with a simple Docker file, where you list all the instructions needed to run your program. So for example, if you are running a simple Python app, you probably want to just install Python first and copy all the code and then run your Python file. If I show you a real example, here you can see two Docker files, one for backend, one for frontend. So if I open up the frontend, you can see I have listed all the instructions to run a React app. So first I'm installing the burn, selecting the work directory, and then copying all the necessary packages, installing those packages, and then selecting the client folder and building the app. And here I have some instructions for static hosting with Caddy. Don't get too deep here or stress out if you don't understand all the instructions here. This is just for an example. For your project, it might be slightly different. Just overall understand that you will need a Docker file where you need to list all the instructions for your program. Once you have your Docker file ready and you build it, it will generate a program which is considered Docker image. It will have everything to run your app. So for example, in this case, we have a Python as a base image, which we instructed on our Docker file. And it will have your code, your ELVs, or any other dependencies you installed to run your program. And this whole thing combined, you can call it Retro UI backend image. In fact, the Python package we are using here is also a Docker image itself. Once you understand Docker image, you might be wondering, how do we find out which image has what name? Like the Python image we are importing here, how do I know that there's a version called 3.11-slim? And that's when you need to learn about Docker Hub. It is a big marketplace where everyone hosts their Docker images. So you can find images for Python, Node, even Retro UI if you want to deploy yourself. To show you an example, you can just go to hub.docker.com and it will take you to Docker Hub website. And here you can see you have tons of images like TensorFlow. This is the Python image. This is the Nginx image. So let's check out the Python one. So Python was installed more than 1 billion times. So needless to say, a very popular package. And if you scroll down, you will see instructions to work with this package. Here's all the listed versions that you can use in your Docker file. I think for us, we probably used 3.11 Slim, maybe this one.
Right
and
now,
this one.
3.14, right?
In fact, I also uploaded Retro UI on Docker Hub, so you can probably find that as well. Yeah, this one. So I haven't added all the documentations to work with it, but if you go to tags, you can see the versions we have. So 1.2 was the latest one. So yeah, that's pretty much about Docker Hub. So let's move on. Once you have your Docker file ready, you build that app and it creates an image. And once you run your image, it creates a container. Think of Dockerfile as kind of a blueprint for your car, which will instruct everything necessary how to build a car. And once you follow this blueprint, you will come up with a car, which is the Docker image. Now, a car itself is useless, right? Unless someone starts the engine and run it. And that's what a Docker container is, where you have your image, you run it, and that creates a container. Let me show you an example. Remember this Docker file we had? This is for Retro UI's frontend. Now, to make it an image, we have to build this first, right? Let me zoom in. Let's close this. Let's run Docker, build, specify the file name, Docker file frontend. We can give it a name of Retro UI frontend, and it's in our parent directory, so we'll go up and you can see it built that image. Everything looks good. Let's clear this. Now let's open Docker desktop. Let's go to images. You can see the Retro UI frontend image here, but right now it's not doing anything, right? It's just a program. We haven't installed or run it yet. So to turn this image into a container, you can directly run it from here. But let me show you how you can do that from a terminal. Let's clear this up. Run Docker, run Retro UI frontend. Before we press enter, we also need to map our container port with my laptop's port. So we can just specify -p, and our port is exposed on 3001. So we'll say 3001, enter. Okay, I think I'm running some other application, so let me close them. Let's try again. Okay, so looks like it's running now. Let's go to Docker desktop, and you can see we have now a functional container. The image it's using is Retro UI frontend, and it's running on port 3001. So now you can just visit this port and you can handle your user requests. Now, some of the things I did might be a little confusing to you, like how do I know there is Docker run or there's something called -p, right? And how do you build your image? That's why the next thing you should know is Docker commands, where Docker give you a set of instructions you need to follow to do certain things. For example, if you need to build your Docker file, you run docker build. If you need to run your image, you run docker run. If you want to stop your container, you run docker stop your container name. If you want to see all your containers, you run docker ps. To see all the options you have, you can just go to your terminal and run docker -- help, and it will list you all the options you have. So you can go through this and have an idea what each of the commands does, and if you have further questions, you can just Google about those. When you start working with Docker, you will soon realize Docker doesn't persist any data. So for example, the container we had, the Retro UI backend, frontend, if I just stop this, it will erase all the data this container had. But sometimes you may want to save data, like if you are running a database and you want to save those data in your local machine, right? Because in case if the container goes down, you still have the data. And that's where Docker volume comes in, where you can instruct Docker to persist data for certain containers, and it will save those information in your machine somewhere managed by Docker volume. So in cases where even the container shuts down, you will still have your data. The next thing you should learn is Docker Compose, which will help you to manage multiple containers through one YAML file. So for example, here I have Retro UI frontend and Retro UI backend. Instead of running those separately through the commands I showed earlier, I can just write those instructions in a YAML file and run Docker Compose up, and it will turn everything up. And if I just run Docker Compose down, and it will shut down all the containers. It makes life so much easier. So if I show you my example, here I have a Docker Compose for my dev environment. I have listed all my containers inside services. So this one is for backend or API, and this one is for the client or the front end. So if I just run Docker Compose, pass the file location, Docker compose.dev.yaml up, and I want to run it in detach mode, and looks like both of them are up. I have the client and I have the API. So moving on, the last but not the least, we have Docker network. So when you make a container like Docker frontend and Docker backend, each of the container is in an isolated environment. Like Docker frontend cannot directly communicate with backend, and the backend cannot communicate with frontend. And that's where Docker network comes in, which lets your containers talk to each other. So if I use Docker network, my container Retro UI frontend can call the backend container, and the backend container can call the frontend container. And that's what you saw in the log here, that I have a Retro UI network. So if I show you that in example, I have this production compose, and here you can see I have created a Retro UI network and added that in the client and in the API, and also including my web server. So all my containers can now talk to each other. And yeah, that's pretty much it. There are other nitty-gritty stuff you will need to learn as you get more experience.
So I believe
Hi everyone, hope you are having a good day.
I have another, the orchestrations on Linux, which is Kubernetes. But I'm not going to. Yeah. And the other one is Linux kernel superpowers and Linux security. Before we John, for today. I'm going to let's take a look at one more video clips. Linux security. Okay, Cell Linux. Before I forget, you guys need to bring your Raspberry Pi kit next week. My recommendation is that if you are not familiar with that, particularly do not try to give power on any of the device that you receives. I will let you know how you need to do. Your SD card, as I said, it has already operating systems embedded. I mean, pre-installed. Do not try to do some of the applications that I showed to you somewhere, my lecture notes, or video clips, Raspberry Pi OS imager. Don't try to run it because we already passed through that levels, okay? When are we going to use that images? At the end of this semester, when you are done, and when you are ready to return your Raspberry Pi back to the department, then I want you to clean up your SD card and put it back to pre-installed, like you received today. So I want you to put it back to the initial state of your SD card. Don't worry about that. We will do that, okay, all together. So you can freely use up to that points when you know. Yeah. So next week we'll do installation and configuration and set up network. I want you to bring the monitor, extra monitor. I know some of you have extra monitors, right? When you have some of the monitors side by side, extended your laptop monitors. I'm not sure how many of you, but usually computer professionals usually use this monitor is small, right? So you have to extend the one. One of the things that here's the thing that if you are interested in, I can show that monitor to you that I like the most. If you want to look for. Extender. Not like this. Oh. The one that you may like, the one that I like from my experience, possibly something like this. Like this. This is a monitor itself. This is not a computer. That's why this is about $50, right? Directly, your monitor can be displayed on that extended monitor. So if you are interested in that one for your laptop, if you have already, or if you plan to have it, bring it. So we can use that monitor to install and configurations of your Raspberry Pi. One time only, one time. One time, once you set up here, then next time you don't need to bring it. Okay? I'm going to bring my small monitor. You can, after I give a demo, I'll let you use it. But we have, maybe more than 10 students with me. May not use that all. So if you have any, please bring it. And also we can use one of the monitor there on our, not all of those. I know one, you can use it. Even so, you need to bring your mouse and keyboard. Mouse here, keyboard, right? I can let you use mine, but still it take turn, right? If you wait to use something that I bring, it takes time, or you cannot finish next week. So if you have an extra monitor, extra keyboard, extra mouse, bring it just one time next week, so that also yours can be shared with others. That's my special announcement for you before we adjourn. Okay, this is I skipped some of the video clips, and let's look at this.
Hi, I'm DJ Ware, and this is the Cyber Gizmo, and today is Wednesday, and Wednesday is tutorial days. I've had a number of people that have been asking me to do a tutorial on SE Linux. Wow, that's a complicated subject. So let's talk a little bit about what SE Linux is. So SE Linux stands for Security Enhanced Linux, and it is a powerful thing called mandatory access controls. You might also see it listed as MAC, M-A-C. Those are systems that are integrated into the Linux kernel directly, and then there is a package around it which helps you to identify and create policies that the kernel will then take and enforce. So, and those are strict policies, and those manage what users can do, what applications can do, and who gets access to what files and what directories on your system. Also, you can secure hardware resources as well. The whole purpose behind SE Linux is to just add a layer of security beyond the traditional Linux permissions. And if you're curious, Linux permissions are called DAC, discretionary access controls. I have heard so much confusion around ACLs. That's the extension to DAC. And those are FACL, get FACL, set FACL. Though the ACLs are part of POSIX, and they are an extension to DAC, but they are not MAC. They are not mandatory access controls. If you're setting permissions on a file, you're setting it for a group of users or a particular user, or you're opening it up to the world. Now, ACLs have a little more fine-grained control. FACLs, you could do, that group I'm going to give read access to. That person is an administrator. They're going to get full access. That particular user just gets read access, or in some cases, that person only gets write access. That is, they can submit text, but they can't do anything with it. DAC is the default security model in Linux. And that is, it's the familiar chmod and chown. Those are the things that you change the owner, you change the mods, or the permissions. It's flexible, but, it's kind of old. It goes back to the Unix days. And you can misconfigure it pretty easily and end up opening things up that you never intended to. And you can grant broad access capabilities, which is never a good idea today. And mandatory access controls allows very fine-grained controls. You can enforce them system-wide. You can make them administrator-defined. You can create policies that can't be overridden by anybody on the system. So yeah, SE Linux uses labels and a combination of labels and security contexts to decide whether access is allowed or not. The other problem with ACLs is that they're still controlled by the file owner. if I own the file, I can do what I want with it. I can grant permissions to whoever I want. That's why it's called discretionary. What are we going to do today? So you could set up Red Hat, you could set up Debian, you could set up Ubuntu, but here's the thing. If you're using a Red Hat based system, it already comes, usually they come already pre-installed with SE Linux already on them. If you're bringing in Debian or Ubuntu, they typically use AppArmor. So AppArmor is a different thing. I did a video, you can see about it right there. I'll put a link to it, so if you are interested in looking at the differences between the two, it'll explain it. AppArmor is a lot easier than SE Linux, but I did see some comments in that video where I use both. That's a really bad idea. I wouldn't do that. You need to pick which one you're going to use. Don't use both. The reason why you don't want to use both is you could leave gaps in your security and unintentionally because you think AppArmor did it or SE Linux did it. The other problem you have is if you get a condition where a file is getting permission denied, it's not allowing you to write it or you're having issues trying to move it, you don't know which one of the two did it. So do yourself a favor. Don't install, make a choice. And I'll make it easy for you. If you're on Fedora or Red Hat, use SE Linux. Or Rocky or Alma, or Euro Linux, or even Oracle Linux, use SE Linux. It comes out of the box. It's already set up. It's already enforcing. If you're on Debian or Ubuntu, use AppArmor. But here's the thing: if you're on a server, use SE Linux. If you're on a desktop, use AppArmor. Again, there's not every use case that's going to fall neatly into those two buckets, but for me, that helps. I mean, it keeps my sanity as I know where I can expect to find something and where I can expect not to find something. So the other thing that we're going to do today is we're going to use Fedora 41 Workstation to install this today. And we're gonna play around with a couple of ideas with a web server on how you can protect the directory that you're serving your web pages from. So I'm going to make a couple of suggestions. If you're new to SE Linux and you don't understand, what the hell are you talking about when you say Mac and DAC? I don't understand. What do you mean? There's a book that Dan Walsh did. It's free. I think you can find it out on the Red Hat site. It's called the SE Linux Coloring Book. It's not very long. It's about, 15 pages long or so, but it's for people that are totally new to SE Linux, have no clue what they're totally beginners to security on Linux, but it'll go through and kind of in a gentle way, using dogs and cats basically to explain how things work. And once you get past the introduction today, my suggestion is there's a couple of books. I'll put the links below for you. There's the SE Linux Administrator's Handbook, and there's also one is called SE Linux by Example. Both of those books have been around a while. SE Linux hasn't changed all that much in the years. They have some things that they have added on to it, but and you can, if you don't need a tutorial kind of approach, you can always go to the Red Hat site and pull down their SE Linux manual. They have a good one. They have one for every version of the operating system. Second piece of advice I would give you is if you're going to mess around with SE Linux, don't use your workstation. Don't use one of your production servers. It's all too easy to get something wrong. All it takes is a typo, and you could block yourself right out of your own system. So yeah, just be aware of that. I mean, I don't know how many times when I was first learning SE Linux that I would blow myself out of the water, lock myself out of the system, and then I couldn't get back in to do anything and ended up having to reinstall it. Well, I don't want you to have to do that. So my suggestion is go get yourself, if you don't have a virtual manager, go get VirtualBox. I use Proxmox, so that's what I'll be using today to set up my virtual machines. I would suggest 2 CPUs, 4 gig of memory, and 20 gig of disk, maybe. For this exercise, I can't imagine it would take more than that. And then after you get it built, take a snapshot of it so that you, if you do make a mistake, you can roll back. And then and that's in case something goes wrong. All right, so let me go get set up, and let's come back and let's start walking through it. The first thing you should always do is make sure it's up to date. And I'm going to probably have nothing to update because I'm using everything, which basically is a network install. So yeah, I should get all the latest stuff already. So I'm good to go here. So the first thing, let me just clear this mess off. So the first thing you should do is, now you can do it this way, SE secure and status, SE status. And you may not get exactly the same thing. Yours might say disabled, or it might say enforcing, but SE Linux status is enabled. It has my mount. It shows the root directory. The policy name is targeted. That is default, and that is what you want. If you see anything other than this, yeah, you might want to go and check. There's the config file, and in there you'll see it says SE Linux is enforcing. You can set it to 3 settings. You can disabled, or you can set it to permissive. And then SE Linux type is targeted. It can be targeted minimum or MLS. We're going to leave it at targeted, and that means that the processes that I specify are protected. And the next thing, we don't need to, I can do this just to make sure that I have everything installed. I want SE Linux policy, SE Linux policy. This is one of the types that we have, and then I want policy core utils. And it should come back and say they're already installed and there's nothing to do. When would you use permissive? Permissive is really good to use when you're debugging because it won't lock you out of the system. It won't actually protect the file. It just tells you what it would have done. Sort of like, I'm just gonna run this through in a dry run situation, and that's kind of what you're doing with it. All right, so like I said, we're going to set up an Apache, and we're going to secure the //www.html. So yeah, I did that the way you said it in the 90s. But in case you were wondering, and I'm going to install the HTTP. This is Apache, obviously, and I'm going to do a system control enable now HTTPD, and then we can check. The status on it, make sure it is up, and it is. Okay, very good. So there are security contexts. A security context is, you can think of it as, this is the policy that I'm using to protect a resource. So you have a label and you have a context, and together those are what permits things to be protected. See, so let me show you. Let me show what I mean. Let's go and look. So if I do a normal ls, I get the normal directories, right? But if I do an L capital Z, I get some extra stuff here. This is your context. this up to the colon. So there's u object r http sys content underscore t. So this is the context this is the targeted context for HTTPD, which means that files in here that match that context on the directory are allowed to be accessed. If I have a file in this directory that doesn't have that, then it won't be accessed. So yeah, that's the idea behind it. The first thing we want to do is we'll do a change context, chcon, and this is the target and its default. And now we're going to set it on var www HTML. Sorry, gotta do it the way you do it in the 90s, because that's the way they said it. Dub. All right, so now again, I don't see nothing. Now I should see default instead of the HTTPD sys context. Now I get default. So what happens if I create? Okay, so I created a file real quick, and so it's in there, index.html. So if I go after that right now, first of all, let me show you this. So we have unconfined, we have object R, and we have our HTTP sys content underscore T. That's our targeted protection. So this should, yeah, it brings up my test page. So all good. Everything's good. I know it's kind of stupid, but hey, I'm just trying to test it. That's all I'm trying to do. All right. So, okay. So what we're going to do now is we're going to screw things up. We're going to set our context to -t default under T, and we're going to go var www.html. Yeah, you got to do it the way they do it, and then index.html. No, that's not going to work. Let's try this one. Okay, now let's look at now we have it set default. Now let's go back here and see what happens. It doesn't like that, does it? It didn't like it. Now, if I look in my, see the warning coming up. SE has detected something. Okay, and now let's go here. I should get my test page back. Ta-da! So that, I know this is a quick lesson. I'm just doing my job to get you to look for yourself on how to do this stuff, because I don't know what you're trying to do. You do. But there's a lot of things you can protect with this. I mean, you can protect cache files. You can protect zone files. You can, if you're DNS, you can protect your Samba configuration so that somebody can't open it up or inject malware into your the directory where you have files that are being shared. So there's a lot of different uses for this, and my advice is, if you're using Fedora, you can, and you just want the user guide, Fedora has one as well that's specific to their distro. There's also one on the SE Linux project website. I'll put all these links down below for you. And then there's the books are SE Linux by Example. That's by Frank Mayer. And there's one by SE Linux Systems Administration. That's by Sven Vermeulen. I think that Vermeulen. I don't know. And those two books are kind of pricey, but the way I look at it is, this is something you're doing every day, and you need to be sharp in it. You need to understand all the different kinds of things and how you can apply use cases. So I've kind of given you, so my final thoughts are, start with a VM. That's safety in mind, because remember, you can lock this is like a firewall that if you misconfigure it, you could lock yourself out. whether you pick SE Linux or AppArmor, that's up to you, and whatever your use case is you're trying to solve. I mean, AppArmor is different. It is, yeah, it's not the same. They are not the same. SE Linux is more difficult but goes deeper. AppArmor is easier, but it doesn't go as deep. You can't do as much with AppArmor as you can with SE Linux. The other thing is practice and learn these techniques and go through it. You can start with policies that already exist. There are GitHub sites where you'll find policies for different types of software.
Okay. I'm going to stop here. Anybody has any question, any comments? Okay. Then this is it for today. And then next week, I'll give the Raspberry Pi to those who do not receive it today. And then those who receive it today, I'll bring them next week. And then next week, we will do real installations. Okay? See you next week.